Greetings all, welcome back. Now I want to do an example of an autonomous differential equation where we can do a brief analysis and say a lot about the long-term behavior of all solutions without doing a lot of work, certainly without solving the differential equation. So here's our example. Y prime equals 1 minus y quantity squared times y minus 4. And I'm going to call that my f of y. In order to basically use this f of y, I want to be able to graph this and I want to be able to talk about it. But I want to make sure you understand that this is an autonomous differential equation because it's written in a form y prime equals some big mess, which is really nothing but a function of y. T is not explicit in the differential equation. It shows up in a dy dt, but it's not actually a variable in the differential equation. So this is an autonomous differential equation. Now, I've made my life easy for myself by factoring this polynomial. But we do know some things immediately, right? We know that because the right-hand side is a polynomial, polynomials are continuous everywhere. And not only that, but they're differentiable everywhere. And the derivative is just another polynomial, which is continuous everywhere. So I know that solutions exist and are uniquely defined everywhere, on all of R, for all Y, in R, and such. It's a good quality to have. That means that solutions can never meet, can never cross. They can asymptote to each other, but they tend to trap each other too. So it's kind of a nice feature for these particular differential equations. Okay, so here, what are the critical points of this guy? Well, okay, this polynomial is already factored, so it does make life easy for everybody to know that the critical points are at y equals 1 and y equals 4. I could graph this guy if I wanted to, and I would have, let me put this up a little higher because I know what this guy looks like already. And if I graph this guy, it kind of looks like this. I've got 1 here, and I've got something akin to 4 here, modulo scale. And you see that my solution kind of looks like this. And this is f of y. Okay, you can see right away it's a cubic, so it'll have at most 2 turnaround points. In this particular case, it does. But it has a particular structure. This critical point here is of order 2. This critical point is of order 1. That's going to be actually useful for us into finding out what's going on. But here's our general graph of f of y. And we know that it touches the x-axis or touches the horizontal axis at y equals 1 and y equals 4. I could immediately start to think about things like a phase line for this. By doing nothing more, and once you get good at this, practiced at it, you can see right away what's going on. I know that I have equilibria at 4 and 1. And I know that here, f of y is less than 0. And I know that here, f of y is greater than 0. And I know that here, f of y is less than 0 again. So I can say right away that this also tells me that y prime is less than 0, which means in terms of y, as t increases, y decreases because y prime is less than 0. So I know that I'm moving in this direction. All of my solutions are losing y values as time is increasing. I know here I'm increasing, and I know here I'm also decreasing. So this is my phase line, and we can see this right away. If I wanted to instead actually look at solutions, I can go into my slope field. And if I go into my slope field, I know that at 1, I have an equilibrium solution. And at 4, I have an equilibrium solution. And in between, I know that all of my solutions here are decreasing in between 1 and 4. So I already know what's happening here. I know that all of my solutions are doing something like this. And I know that every solution is doing this. And I know that every solution is doing this in this particular guy. These guys never meet, but they do sort of asymptote all to this horizontal guy out here. I know that these guys are increasing, so I know that my solutions here are heading up. Here. And I know that now if I pass down below 1, I know that I'm also heading down, so my solutions are heading down this way. And they have to head down steeper and steeper and steeper because there are no, this is just a polynomial, so it has to behave a certain way and such. So I can say what all of my solutions are basically doing. Basically just on this knowledge, I haven't calculated any solutions here, but I can draw them at least schematically, if not so accurately. And then lastly, I can easily say, hey, what happens to the long-term behavior in my solutions? What happens as t goes to infinity of y of t? And I can grab my individual pieces that way. I can say that I'm going to minus infinity if y0 is less than 1, because I'm here now, and I know if I start with a y0 less than 1, there's nothing for me to do but go to minus infinity. I know here I'm going to be at 1 if y0 equals 1. Right? That's this guy here. I know if I'm larger than 1 and less than 4, I'm heading down to there. So I can basically say that this is going to be 1. I will edit this because there's more things going to 1. And I will say now that as long as 1 is less than or equal to y, well, this is y0, right? As long as y0 is less than 4, I know I'm heading to 1. 1 will stay at 1, but everything less than 4, hard less than 4, right? The inequality less than 4 heads down to 1. So I've got that guy covered. I know that if I'm at 4, then I'll never leave 4 because 4 was a critical point of this guy, so it corresponds to an equilibrium solution at y equals 4. And then I also know that everybody else, the only guys that are left, y0 is greater than 4, heads off to infinity. And really, I knew that just by grabbing this guy and graphing it and understanding how to produce my phase line. I don't really even need this, although I can actually draw more or less what my solutions look like just because it's an autonomous differential equation and it has the properties that I want. But this piece down here gives me a good sense for what the long-term behavior is given an initial condition. Now I know that if I start with any particular initial condition, I can say, let's say, ooh, I'm here and y of 5 equals minus 1. Well, when t equals 5 or t equals 40 or t equals minus 16, all of my solutions are doing the same thing. The only part that's important is this way, and the conclusion you can draw is, well, I don't know what my solution looks like moment by moment, but I do know because my y0 is minus 1 that I can go to this chart and say, ooh, I'm below this guy. My solution is going to blow up, or what does it mean to go to minus infinity? Blow down? I'm not quite sure, but it's going to basically head to minus infinity. So without solving anything, I can say immediately what my long-term behavior is for this particular solution. This guy here is unstable, and this guy here is semi-stable, because it's stable on one side and unstable on the other. The idea is if you wanted to hit your initial value at 1, but you didn't have good resolution, you might want to cheat to numbers larger than 1. and make sure that you start your initial value with a number slightly larger than 1 so that you know you'll veer down to 1. Because if you start anywhere less than 1, well, you're toast. Anyway, that's enough for this now. This is a nice example. And you'll do some more examples in homework and such. But for now, thank you for listening. And we will talk again very, very soon.